Today's lesson is all about balance. And how do we find balance? Do we find balance by using our fingers or our toes? Do we find balance with cardboard or rulers? It's an important thing. Now, please note, I am not talking about the Chinese Zen type balance. I'm talking about balancing objects and how one little very important thing is important in balance. Welcome to CSEC Physics with me, Marvin Lee. Balance. Welcome again. In today's lesson, we will be looking at center of gravity. Center of gravity. Center of gravity is defined as the point on an object or body through which its weight is considered to act. Now, you might be thinking when you hear that, like, ain't the whole body got weight? Yes, the whole body has weight. But an object's center of gravity, or you could say center of mass, is the point at which or through which its weight is considered to act. It's the point through which or at which you can actually balance the object. Classic examples. I'm sure you've seen figure skating when it's couples and a man is figure skating with a woman and he does that thing where he lifts her up with one hand and they go sliding across the ice. If his hand is not directly under her center of gravity, she will topple, fall, and they will both get injured. Now, center of gravity is very, very important and highly underrated. It's something that is taken into consideration more often than not. Everything from fancy furniture to buildings to Formula One cars to how boxes stand. All of these things involve considerations of where your center of gravity is. So, please don't take it for granted. Please stay tuned. We have an interesting lesson today. You probably remember my friend Brown from the start of today's lesson. Now, there are several factors that influence where an object's center of gravity would be located. There is this, well, it's not a concept. If an object is regular in terms of its sides and internal angles, you will find its center of gravity located at its geometric center. So if you have a square, if you find the dead center of that square, your center of gravity would be located there. If you have a circle, center of gravity would be located at the center of the circle as well, because those are regular shapes, so to speak. Now, another fact is if the object is uniform or not. Now, uniformity simply means is mass evenly distributed throughout the length of the object. So if I cut this piece of cardboard into, let's say, 4 equal lengths, well, each length have the same mass. If each of those 4 lengths has the same mass, we say that the object is uniform because its mass is evenly distributed throughout its length. Now, these factors are very important because if an object is irregular and if it is not uniform or non-uniform, you will find that its center of gravity will not be located in its center, geometric center. Its center of gravity will be located elsewhere. Essentially, if one side of this cardboard had more mass than the other, the center of gravity would move to the side that has the greater mass. So, regular and uniform, 2 factors which influence where an object's center of gravity would be located. Now that we know what center of gravity is and what regular and uniform mean, we can move on to stability. Now, the location of an object's center of gravity affects how stable it is. Now, you can simply say an object is either stable or not based on how easily it topples or basically rolls over. If an object is able to withstand a large amount of force and not topple, it's very stable. If slightest breeze makes it change its position, you can say it's relatively unstable. Now, objects with good stability have low centers of gravity. Boxes have a wide stance where their feet are not next to each other. One is slightly ahead of the other for a reason. That's to allow them rather to throw a punch and also to actually take a punch without toppling over. If you stood with your feet close together like you're a soldier, your hands at your side, and somebody gently pushed you and you did not react, you would easily topple over. However, if you widened your stance, one leg slightly in front of the other, you are actually going to be far more stable, and a push is not going to move you. Vehicles. Low, wide vehicles are far more stable than high, narrow vehicles. It's the reason you don't see small, narrow, and high supercar. You don't ever find that. Supercars are flat, wide, and they are flat and wide for a reason. Because again, at those speeds, you need to be able to be stable. Same thing with Formula One cars. They're very low, they are very, very, very low, and also they're very wide. That means if you're taking those cars around a turn at ridiculous speeds, you're not going to just flip over, because again, they make them to be stable on turns. Now, I have brought with me a slinky. You might be thinking, Lee, why did you bring this to teach us center of gravity and stability? Well, if I took my slinky and I put it down on the table and I try to make it as vertical or as straight as possible, it wouldn't easily topple. However, if I gradually just displaced a few of the rings, I would get to a point where if I just gently pushed it, it would topple over. Now, the reason it topples so easily when it's in this warped or deformed shape is because of the fact that as I move the rings out in this direction, the mass or the weight moves with the object as well. And eventually there comes a point in time when the weight no longer acts through the base. Now, the base is the area in contact with the tabletop. So if I keep displacing these coils or rings and I get to this point, it will just topple. Because again, the weight is no longer acting through its base. This is why a wide base is needed. The wider the base, the greater the area in which the weight has to act. And if the weight of an object acts through its base, the object is way more stable. Way more stable. Now, there's three types of stability that we have to look at. We have stable equilibrium. Now, when an object is defined as stable, it means that you can displace it from wherever it is. You can give it a push, and when you stop pushing, it's going to go back to its position before you pushed it. Okay? Classic examples are drums of water, full barrel or a drum of water. For those of you who never had the experience, nothing beats playing with a barrel full of rainwater. All right? Those things are very, very fun to have. Lovely old Guyanese custom. Now, if you have a full barrel or drum and you gently push it, it will wobble, but most times it goes back to where it was before you pushed it. That means it is stable. Some chairs are like that too. You push them and they tend to go back to how they were before you push them. Then we come to objects that we can label as unstable. My best example, the example I love, is in the Minions movie when the Minions made the pyramid and they had the pyramid on its apex. And Pharaoh opened the pyramid with grand fanfare and the pyramid crushed him. Now, the pyramid was balanced on its apex, yes it was, but at the same time, that was unstable equilibrium because any slight application of force would have displaced it. The thing about objects that are unstable is that they tend to seek stability. I know this sounds so Eastern and so Zen, but that is the truth. If you displace an object that is unstable, it will try to find a place of stability. And then finally, we have objects that are called neutral. Now, neutral objects are objects that keep their centers of gravity at a fixed distance above the Earth's surface. A barrel on its side, a ball. Two best examples. These objects, the height of their center of gravity above the ground remains fixed. So please remember, objects can be classified as stable. They return to their positions after being displaced. Unstable, they find new positions after being displaced. And neutral, everything looks the same even when they are displaced. The syllabus requires us to perform a lab where we find the center of gravity of a lamina. Now, a lamina is a flat, two-dimensional shape Okay, flat two-dimensional shape, or as close to flat as you can possibly get. Well, and two-dimensional too. Now, the easy thing would be to find the center of gravity of something regular, like this, my piece of cardboard. However, just for the sake of being difficult, making life difficult for me, I will make this horribly irregular. You know, just trim a little here and some there. Maybe take a piece off here and probably do this as well. Now, I am not sure you'll ever find something that looks like this in a textbook. This is as irregular as you can possibly get. This is our irregular lamina, and we will now find its center of gravity, or the location thereof. And its location just might surprise you. Now, what do we need? Well, I needed a scissors to make my lamina, and of course, I needed a piece of fairly sturdy cardboard. I need another piece of cardboard. This is very important, and a second piece of cardboard. I have what is essentially a simple pendulum, but it's called a plumb line. Now, a plumb line is, like I said, a simple pendulum, mass, light, and extensible string. And for those of you who have ever seen people do any form of construction, you would commonly see them using this when they're putting up posts or columns. This is actually used to determine if structures are vertical, because any pendulum left suspended freely will actually give you a vertical line. Now, one of these, and you could actually use anything as a mass. You could, as long as it has decent weight to it, an eraser, probably tape some coins onto a piece of string. All of that works as well. So string, mass, plumb line. Our ever trusty, faithful retort stand. And a paper clip. Yes, a paper clip. Now, what do we do with all of this? Let me show you. So, one of the first things we need to do is establish a few points on our irregular lamina. Now, I will show you it using this. If I held this object, actually no, I'll show you using this. If I punched a hole through my very sturdy, apparently, lamina, this thing is so sturdy it's bending the paper clip. Good. So I have a hole and I have my very irregular shape. Now if I try holding the shape like this and I let it go, it rotates freely about my paper clip. What happens, or how we go about doing this, is if you suspend an object and that object can rotate freely about its point of suspension, you will find that when it comes to rest, its center of gravity is directly below the point of suspension. So when I suspend this and I allow it to freely rotate, the center of gravity will be somewhere below this point of suspension when this object is at rest. That is the basis behind this method of finding an object's center of gravity, which is, for your information, called the plumb line method. So what I will need is to make a few points along the object, at least 3. I will have to suspend my lamina from each of these 3 points, and I will have to mark the location of my plumb line. Let's do this. This is really harder than I thought. All right, my cardboard is beaten my poor paperclip senseless. All right, please don't laugh at me. If you're laughing, laugh with friends, okay? Just don't laugh by yourself. I hope they edit this out. I really hope they edit this out. Alex, please edit this out. If you don't, my students are going to laugh at me. He isn't going to edit this out. I just know that. It's just going to come back to haunt me. You know what? By the magic of editing, I'll be back. Ha! Thank God for sharp objects. If my students see me say that in the video, they would actually be like, yep, this is our teacher. All right. I have made a few holes in my lamina. I have 3 of them, as you can see. Now, 1, 2, and of course, 3. If you see me sweating, I'm sweating because the fans have been turned off. Now, why have we turned off the fans in the lab? Because wind can actually influence or prevent our lamina from coming to rest. So this lab might make you sweat a bit. Anyways, now that I have my points of suspension, with a pen, I label them A, B, and C. Now, this is important because you have to remember, or you have to mark them so you know you suspended it from which point, when, and you go through them in correct order as well. Now, if you don't have a paper clip, you could use a pin or a needle, but please be careful with the pin or the needle. I don't want anybody poking their eye out and then your parents come in to accuse me of making you blind. That's not the case. That's not what I was trying to do. I was trying to help you with science, not blind you. Now, I folded my other piece of cardboard and I'm using that to basically hold the paper clip. Because the paper clip has to be a fixed point, you really can't hold it in your hand. So folded the cardboard, put the paper clip in it, and now I will put this in my retort stand. All right, so very simple. Retort stand. Let me turn this to you slightly. Let me open this. Boy, does this thing rattle. And here I have my nice little point of suspension. Tighten this, make sure it could face the camera and all of that. And let me come around now. We have our lamina with our 3 points A, B, and C. Remember, note and remember that it has to be 3 or more points. Cannot be less than 3 or more. A, B, C. You can have D and E if you wish. It would just make the location more accurate. But for time, I've only used A, B, and C. What we do is we suspend our lamina first. And again, notice it can swing freely from our paper clip. With our lamina suspended, we now have to suspend our plumb line. They're suspended from the same point. This means that somewhere along this string, or the line made by the string, we have the location of our irregular lamina's center of gravity, okay? This does take some time to come to rest, and it would take a lot more if there was wind interference. So what I normally do is try to help the system by bringing the pendulum to rest. And with a pen or a marker, you don't come and hold apparatus with both hands, because clearly you see you put it into motion again. When the system is at rest, you can clearly see where it crosses the edge of the lamina. Now, you know the string starts at point A and crosses the lamina somewhere here. If you're skilled enough to just use your pen and mark the lamina, go ahead. If not, you can gently, very gently again, please don't grab it with both hands, mark where the string crosses the edge of the lamina, the edge of the lamina. You remove the plumb line you remove your lamina and you draw a straight line from point A to where the string crossed the edge of the lamina. Now, this can only be made from point A to the point where the string or the plumb line crossed the edge of the lamina when suspended from point A. Okay, so I would recommend that as soon as you take it down, you draw your line. We will now draw our line. And I forgot my ruler. Oh, Father. This is a slow day for me.
Yep.
Being in a physics lab, we have the best rulers in the world, a meter rule. We ensure that our ruler is in the correct place. We ensure that our ruler is in the correct place, passing through the point of suspension and the little mark made on the edge of the lamina. And we draw a line. That's our first line. We take our lamina, place it on our paper clip again. If I can find the... Aha. It's suspended from our second point with our plumb line. We suspend it from that second point. And we let the system come to rest. Again, you can gently influence the behavior of the plumb line. And there I was breaking my own rule about being gentle. Good. Position of plumb line across the edge of the lamina when suspended from point B has been marked. Remove plumb line, remove lamina, break out our trusty meter rule, ensure that it is where it should be. We draw our second line and we repeat for our third point. We suspend it from our third point. Again, we suspend our little plumb line. And if you notice, just by looking at our lamina, we see that if it just comes to rest, we see that the string passes through the point of intersection of the two lines previously drawn. Now, that means that I think I did a good job. So I mark the location where the string crosses the edge of the lamina when suspended from point C. I remove my plumb line and my lamina, and now I draw my line. Now, there are errors in this lab of simple but significant nature. Everything from allowing the system to come to rest, to marking where the plumb line crosses the edge of the lamina, to drawing the lines introduces some form of error. And here we have our three lines intersecting at one point, and we do the great one finger test. Does it balance? I hope I don't embarrass myself. I think this is close enough to balanced. It balances. So whenever you're finished finding the center of gravity of a lamina, regular or irregular, always attempt to balance it, just in case. Sometimes the results shock, surprise, and maybe even embarrass you a bit. But here it is. We have our lamina perfectly balanced. So, in today's lesson, we looked at center of gravity. We defined regular and uniform. We looked at the three types of stability, or equilibrium: stable, unstable, and neutral. And we found the center of gravity of an irregular lamina. Center of gravity, it is your friend, but if you take it for granted, it can be your enemy. I hope you learned, I hope you enjoyed, I hope you had fun. See you in the next one.